Okay, Assalamualaikum and good morning to our lecturer. So today we'll be presenting about valence bond theory, and for my part, I will be presenting about the objective, introduction and conclusion. For the first objective of valence bond theory, it is to explain the background and history of valence bond theory. So for the second one, to describe how orbital overlapping and hybridization contribute to bond formation and bond strength. For the third one, to discuss the factor affecting orbital overlap between covalent bonding. For the last one, to evaluate the limitation and significance of valence bond theory. That's all for the objective, and I'll be talking about the introduction. So for the introduction, valence bond theory is a theory used to explain how atoms form covalent bond in molecule. It describes bonding as the overlap of atomic orbital, where electrons of opposite spin are shared between atoms to achieve a stable molecular structure. Fun fact, valence bond theory is one of the earliest theories to explain why bonds have specific direction and strength.
Principle of valence bond theory. According to valence bond theory, a covalent bond is formed by the overlap of half-filled atomic orbitals of two atoms. Each atom contributes one unpaired electron, and when there are atomic orbital overlap, these electrons pair up with the opposite spin. This pairing lowers the overall energy of the system, which makes the bond more stable. The overlapping orbitals share a localized electron pair in the region between the two nuclei. This shared electron density creates a strong electrostatic attraction between the positively charged nuclei and the negatively charged electrons, resulting in bond formation. A key point in valence bond theory is that bond strength depends on the extent of orbital overlap. The greater overlap leads to higher electron density between nuclei, which produce a stronger covalent bond and therefore a higher bond energy, which means more energy is required to break the bond. Next, valence bond theory explains how and why atoms form covalent bonds by focusing on atomic orbital and their overlap. Atomic orbitals are not all the same, but differ in shape, size, energy, and orientation, and these differences directly affect how atoms bond with each other. A covalent bond forms when two atomic orbitals overlap, allowing an electron to be shared between the atoms. The greater the overlap between the orbitals, the stronger the bond formed. This is because the stronger overlaps mean the electrons are held more tightly between the nuclei. There are two main types of covalent bonds. Firstly, sigma bonds. Sigma bonds are formed by head-on overlap of orbitals along the bond axis, which makes them more strong. Second, pi bonds. Pi bonds are formed by side-by-side overlap, and because this overlap is less effective, pi bonds are weaker than sigma bonds. Smaller and more complex orbital overlap more efficiently, which result in stronger bonds. Hybridization such as sp, sp2, and sp3 also increase overlap by creating orbitals that are better oriented for bonding, further increasing bond strength. Overall, stronger bonds tend to have shorter bond length and higher bond energy, meaning more energy is required to break them. There are several advantages and disadvantages of principle of valence bond theory. Advantages are explain bond formation clearly. Next, explain directional natures of bonds, and explain hybridization and molecular shape. Lastly, useful for understanding organic molecules. Disadvantages. First, cannot explain magnetic properties of some molecules such as oxygen. Next, does not explain delocalization of electrons well. Lastly, less accurate for complex inorganic compounds.
Hybridization is the mixing of atomic orbitals with similar energy, such as s and p orbitals, to form new hybrid orbitals. These hybrid orbitals help atoms form stable bonds and explain why molecules have specific shape. This is example for hybridization. For CCl4, carbon has a valence of 4. After electron formation, carbon undergoes sp3 hybridization and forms 4 sp3 hybrid orbitals. Each orbital forms a sigma bond with a chlorine atom, producing 4 single bonds. For NF3, nitrogen has a valence of 3. It undergoes sp3 hybridization to form 4 hybrid orbitals. 3 orbitals form bonds with chlorine and 1 orbital contains a lone pair. For CH4, each carbon undergoes sp2 hybridization. 3 sp2 orbitals form sigma bonds and 1 unhybridized p orbitals form a pi bond. This creates a double bond between the carbon atom. For CH2, each carbon undergoes sp hybridization. 2 sp orbitals form sigma bonds and 2 p orbitals form pi bonds. This results in a triple bond.
Next is type of orbital overlapping. There are two main types of orbital overlapping. Sigma overlap occur when orbital overlap end to end, such as S to S, S to P, or P to P overlap, forming strong bond. Pi overlap occur when p orbital overlap side to side, usually in double or triple bond, and is weaker than sigma overlap. Next is factor affecting orbital overlapping. Orbital overlapping depend on several factors. First, the distance between nuclei. The closer the atom are, the stronger the overlap. Second is the shape of orbital. Directional of orbitals such as p and d overlap more effectively than s orbital. Third, the orientation of orbital. Orbital must be properly aligned to achieve maximum overlap. Lastly is electron density. A higher number of unpaired electrons leads to stronger and more stable bond.
Okay, next is the limitation of valence bond theory. Valence bond theory have a lot of limitation. The first one will be discussed is lack of quantitative explanation about the stability. VPT only give an explanation in a qualitative way about the coordination compound. It cannot explain the stability of compound in a quantitative way, which compound has more stable. Next, assumption of localized electron. VBT only assume that electrons are localized between the metal ion and the ligands. Because of this assumption, VBT cannot explain the electron delocalization, which affect the bond length and bond strength in some structure. Okay, the third one is fail to explain unpaired electron and magnetism. VBT only give a poor explanation of magnetic properties. It cannot clearly explain why some compounds are paramagnetism while other are dimagnetism. For example, oxygen gas is paramagnetism, which means it attracts to magnetic field. This because oxygen has 2 unpaired electrons. However, VBT cannot explain this behavior correctly. This because it assumes that all electrons are paired in a covalent bond. This shows that VBT gives a poor explanation of the magnetic properties of molecules. Lastly is inability to describe bond strength and bond length in resonance structure. VBT only assumes that electrons are localized in specific bonds. Because of this, the theory cannot explain the resonance structure where electrons are delocalized over one or more bonds. As a result, VBT cannot explain correctly the actual bond length and bond strength, which are intermediate between a single or double or triple bonds as observed in resonance systems such as benzene.
Okay, lastly is the significance of valence bond theory. The first one is orbital overlap. Valence bond theory explains that a covalent bond is formed when the atomic orbitals of 2 atoms overlaps effectively. The greater of the overlapping, the stronger of the covalent bond form. Second one is bond direction. VBT explains why covalent bonds have a specific direction in space. This is because atomic orbitals overlap in certain orientation, which helps us to identify and predict the shape of molecules. Third one is electron pairing. According to the VBT, bonding occurs when electrons with opposite spin pair up in the overlapping orbitals. This pairing increases the stability of molecules. And lastly is concept of hybridization. Valence bond theory introduces hybridization such as sp, sp2, sp3, sp3d, and sp3d2 to explain why some molecules form equivalent bonds. Hybridization helps to explain molecular geometry, for example, linear, trigonal, and valence bond theory provide a fundamental framework for understanding chemical bonding by explaining how atomic orbital overlaps to form a covalent bond. Through the principle of orbital overlap, hybridization, and the nature of atomic orbitals, VBT helps to predict the bond strength, shape, and the geometry of molecules. Despite its limitation, such as unable to explain molecular magnetism and localized electron bonding in molecules, it's still significant in modern chemistry.